I can just start.
The first thing, your first task as organizer.
No, we have to that.
You not go and start.
I just start, right? That's simple. So, yeah. Third part, I think there will be kind of lot of motivation in this game. So I just start with the definition. Okay, why operator algebras? And I will be mostly following notes which says the basics of C-star algebras. So advantage is that I need not write sentences. It means three things. Firstly, there is a Banach space, an associative algebra. That means that there is a product A dot B such that and it is distributed over addition. Thirdly, there is a relation between this product and for all A, B in A. So, advantage of such an object is the following. If we are just having algebra sums like this, in an ordinary associative algebra, everything is. So, in this setting, one can talk of infinite sums. So, in ordinary algebra, without this Banach condition, finite sums, and the Banach condition allows one to talk about infinite sums. This is because of. And then, of course, this simplifies various things, and we will see them maybe later. How does it simplify? So, examples first is complex numbers. Of course, it is a Banach space. The algebra structure is ordinary multiplication. Second is you start with the Banach space, and then Lx is the space of linear operators. Here multiplication is composition, and so with these things Lx becomes a Banach algebra. You start with the compact Hausdorff space and then consider C of x and the continuous functions. They are defined pointwise multiplication. Then Cx is the Banach algebra. So you take two functions f1 and f2 which are integrable and then define their convolution product. Then this is in L1 because, so let us try to integrate this object. And that is So this shows that for almost all x, this integral converges, and the L1 norm of f1 star f2 is so L1 R is a Banach algebra. And this object is part of a bigger family on which I do not elaborate at this moment. So, if G is a locally compact Hausdorff topological group, then there exists a measure which is unique up to scaling mu such that and then if you consider L1 of G with the product then this is a Banach algebra. Now note that except for this example and that,
Just before you erase this, when there is a nice 2-page proof that this last line will be defined almost everywhere. This product in Rubin's book. Or
that's what I did.
yeah.
By Fubini's theorem, I proved that it is L1.
There may be some people who are not familiar with the intricacies.
No, I just did that. So I integrated that and I proved that it is L1, and so this integral converges and its L1 norm is less than or equal to f1, f2. Okay. But note that except in the first 3 examples, all these Banach algebras are unital. So let us say Banach algebra is unital. If there exists an element, say 1 in A such that 1 dot A is A dot 1 is A for all A, and you also impose this condition, then of course this is unital. This is unital because the map identity transformation, constant function 1, but this has no unit. Okay, so in general, Banach algebra did not have a unit. That's a remark. So but we can always kind of enrich this with a unit. So that's another observation, that let A be a non-unital Banach algebra, then define A tilde to be A direct sum this as a Banach space. I define the norm like this, that and product is defined like that. Then of course you can verify that A tilde is a unital Banach algebra. Okay, I'll do that later. Next comes the important definition of spectrum. So henceforth, unless otherwise specified, we will assume that the Banach algebras are unital. If it is non-unital, I will mention it explicitly. So spectrum of A is defined as all those lambda in C such that is not invertible. So an element A is invertible, of course that is obvious definition. So, or say X is invertible if there exists y such that xy equal to yx equal to 1. So spectrum of A is all those complex numbers such that A minus lambda is not invertible, and yeah. This is an exercise. Let us see some invertible elements in the Banach algebra. So let A be an element such that strictly less than 1. Then no, I should state it maybe GLA and A inverse equal to no. So proof is by geometric series. So norm 1 minus A is less than 1. Then this series estimate these norms. Norm this is less than equal to, using this Banach algebra condition, now it is less than 1, so this is dominated by a geometric series, and so this is finite, and therefore that series converges. And now I leave these two as exercises because you put a norm sign and then this is, this proves this, similarly this one. Okay. So suppose this is again the definition. Suppose omega is open in C and the function f from omega to a is analytic if for all z naught in omega there exists open set u z naught containing z naught, that f z is summation a n is numbers come from the algebra A, and we say f is analytic at infinity if there exists some scalar c
Make one comment. If at any stage there's anything that he says that anybody
Yes.
does, you want to probably ask why. For example, everybody understands why that last equation is true. Now, in the first section of the board, now on the left side, there's something is the inverse of A. Does everybody? So if you keep quiet, that means you've understood why it is true. So that requires some work.
requires some work, so you have to multiply.
So anyway, so
What is the response? No, that says this series makes sense, right? But he is saying, why is this the equation?
that's the inverse of A.
Why is this inverse of A? That says that quantity makes sense. So here I am estimating that sum. I am proving that it is a meaningful quantity in the Barrack algebra. But why is this so? So let us leave this. It is you multiply step by step and it should cancel.
I'm not asking you to do it here, but
No.
if you
But here is so let us leave this thing also as an exercise. We will verify it sometime tomorrow. But your response is incorrect. So anyway, so if it is an analytic function, then define like that. And this concept is used to prove this very useful fact. So this is a theorem that in a unital Barrack algebra A sigma A is a
You want to put mod there,
where?
line 2 from below.
Yes. Sigma A is a non-empty compact subset of C. And so this is a definition. The resolvent is this map Z going to say Z minus A inverse. This map is defined on sigma A complement. So if mod z is large, then this implies maybe I should put this entire thing within this, and therefore by that thing 1 minus a by z, this is invertible, that implies and this implies
So let me do my act again. Nobody commented what does GL of A mean? No, I assume in order to understand what GL of A means.
oh, it is. I have erased. No, I have done this here. GLA x in GLA if there exists y, such that xy equal to yx equal to. No, that is fine, but I am doing it quickly. So yeah, sure. So GLA is a set of invertible elements in the algebra A, and so 1 minus a by z is in GLA by that proposition. Norm of this is small, so 1 minus this is invertible, therefore z minus a is in GLA and so on. So this shows that z minus sigma a complement is contained in the closed disk of radius norm A. Yeah, so sigma A is contained in ball of norm A around 0. Now I want to prove that sigma A complement is open. Okay. So suppose z naught minus a is invertible. Yes.
I didn't get why that 1 minus a by z is
Because by that proposition, if norm of something is small, then 1 minus that is invertible. Right? That's what I just proved. The estimate is still there. So, yeah. So suppose z minus a is in GLA, and so let us try to estimate this quantity. Z minus a is but you should do this argument few times on your own, then you will see what is happening. So say you take out of this, so this is like 1 plus I take z naught minus a common out of this, so it is like 1 plus z minus z naught minus a inverse. Now, if I can prove that, of course I know this is invertible, so this is invertible if and only if now this is invertible. So, if mod z minus z naught is strictly less than 1 by norm So if this is true, then again this product has norm less than 1, therefore 1 plus this is invertible, so z minus a is invertible. That says that around z naught, if I draw a ball here, then that is there, so sigma a complement is open. Next part is the most important part. So, and till now it is kind of with geometric series, and this uses a new idea, and which is very important idea. So let us do that. Suppose sigma A is empty, then we can consider this function fz is like z minus A inverse, and let us verify this, that this is an entire function. So for that probably, okay. So I prove that, let us prove this step first, that this analytic here, and then we will come back to that step. So to prove analyticity, we need to start with an element z0, which is on that set. So suppose z0 is here, and then we know that if z minus z0 is strictly less than then, so we can consider u z0, that is ball of radius 1 by and now on that thing we expand this z minus A inverse. So we know and therefore z minus A inverse is like no n So as you expand this, now again you expand it into that geometric series formula, then this shows that this function fz has got this expression. That means that this function is analytic. That is our definition. And again I leave this as an exercise. This proves analyticity at this set if is analytic at infinity. So that proves that f is an entire function. Now we want to prove that f is bounded, okay? So we digress for this lemma, and this is not there in the notes, so maybe you should note down this lemma. This is useful. So let X be a subset of a Banach space E, where E is a Banach space, and X is weakly bounded if for all phi in E star, this subset phi of x is bounded, And lemma says that X is weakly bounded implies X is non-bounded, and maybe I leave its proof. I don't know, should I leave it as an exercise?
You can just bubble those. You can say exercise but bubble those.
Okay, yeah, so you use uniform boundedness principle. So idea is the following: each X, you consider this map, say X star star from E star to C, namely X star star of phi is phi of X. Now, what is this weak boundedness? Proving this weak boundedness says the following, that for all phi there exists something m phi such that kind of supremum over X mod phi X is less than m phi. That means if you consider this family of linear maps X star star, fix a point phi, and then right, this condition and this condition are same. Therefore, uniform boundedness says that now, of course, this is the isometric embedding of E in E star star. So, X going to X star star. So, this is same. Star norm and norm X is same, and therefore, this is M. So, this lemma is useful. Using this, we are planning to show that if we have an analytic function, then on a compact set, it is weakly bounded. And therefore, on a compact set, it will be non-bounded. So, proof, you fix phi from A star, and then you consider this phi composed with f from omega to C. By definition of analyticity, phi composed f is kind of a user analytic function, and therefore, in particular, it is continuous. So, that means that this set Fk is weakly bounded. So, therefore, by this lemma, it is non-bounded. So, what we are trying to do is, we want to prove that F is bounded. So, this F has two kind of behavior. If, let us take mod Z is greater than norm A, this is one region, and another region is mod Z less than or equal to norm A. This is compact. We have proved our function is analytic. Therefore, F of this region is norm bounded. If we can prove that f on this region is also norm bounded, then we will end up proving that f is norm bounded on the whole space. So, therefore, if you and then this is 1 by 1 minus and I think so. Let us take like that. Then in that region, this quantity is less than equal to 1 by norm A. So, by that corollary, this is norm bounded, and f of this region but they together cover C, therefore f is bounded, okay, or maybe norm bounded like. Okay, so what we have got is we have got a function f from C to A, which is analytic, and f is bounded. Now we take an arbitrary linear functional phi on A star and consider phi compose f. Because of this condition, this is an bounded entire function. So, phi compose f must be constant, and what is the value of this constant? So, let us try to compute this limit z going to infinity, and again from this estimate it will follow that this is 0. So, this implies f of z equal to 0, because that it is true for all phi. So, since phi is arbitrary, f z equal to 0, and that is a contradiction, because we know that f z is an invertible element. Okay. So, this is a contradiction. But this trick is very useful, reducing it to a bounded entire function, and therefore, here is an exercise. Let A be a Barrack algebra such that then A is commutative. Yeah, but this is slightly, I mean, it is not an obvious exercise. Are the students familiar with, no, but Rudin, Barrack algebra, that chapter, it is there, it is from Rudin. Okay. So, Now a consequence of that observation that spectrum is non-empty is this, and let A be a Banach algebra in which every non-zero element is invertible, then A is like isomorphic with C, and proof is also obvious because kind of you take, so spectrum of A is non-empty. So suppose, like let us call it lambda A. So spectrum will consist of only one point, because if there are 2 points lambda 1 and lambda 2 in the spectrum, then we know that A minus lambda 1 is not invertible. Both A minus lambda 1 and A minus lambda 2 are not invertible, but 0 is the only element which is not invertible. That says that since 0 is the only such element, therefore lambda 1 equal to lambda 2, and so you have a map from A to C phi, namely phi of A is lambda A and isomorphism. Then second corollary is the following. So that says if I take a polynomial, then spectrum, so what is P of A? Suppose P of Z is like summation Cn Z power n, then P of A has the obvious meaning so this is an element in the Banach algebra, and the proposition says that the spectrum is P of spectrum of A. So then we factorize this quantity Pz minus lambda. This is a polynomial, so you can factorize, and so this is not invertible, means that at least one of these must be non-invertible, because if all of them are invertible, then product of their inverse is an inverse for this. So this implies A minus alpha I, because okay, maybe I write down here Pa minus lambda is C times A minus alpha I. A minus alpha I does not belong to GLA for some I. And now
there is something that was observed here.
what?
There are products of 5 elements.
That's what I just said.
Invertibility is not equivalent to them all being invertible.
That's what I just said. That's what I just said. If it is not invertible, then at least one of them is non-invertible, because if every element is invertible, then the product is invertible. Okay. So again, if each term here is invertible.
I didn't understand how you resolved your dispute.
No, it resolves because it says the following. See, if all of them are invertible, then the product is invertible, hence this is invertible. So it is not invertible implies at least one of them is non-invertible. That's it.
He's saying he's only making one base shape, not a different ordeal shape.
No. So A minus alpha is not invertible, and now what is lambda? Lambda is P of alpha I. Okay. So it says that lambda belongs to spectrum of PA implies lambda is from P alpha I, where alpha I is in spectrum of A, that is spectrum of PA is contained in P of spectrum of A. Okay. Now suppose lambda is on this side. So lambda is P of alpha, where alpha belongs to spectrum of A. Okay. Again, so let's suppose Pz is like summation Cn z power n. So Pa minus lambda is like Pa minus P alpha is like summation A to the power n minus alpha to the power n times z power n, and this is equal to A minus alpha times another quantity, and
Suppose Cn becomes z power n.
no, okay, let us see, yeah, sure. So it is, point is that all these things contains A minus alpha as a factor, and you pull it out, and then we know that A minus alpha is not invertible, and therefore Pa minus lambda is not invertible. Huh?
U star u is 1.
No, let us think. So if AB is invertible, if and only if both A and B are invertible. So let us try to prove that. It is commutative.
That is the crucial word which you left out. AB is invertible is not different.
Oh, sure. So, okay. Yeah, so let us put that, and then AB is invertible. A and B are invertible. So why is that? So yeah, meaning there is nothing really. Right? If ABC is 1, then of course you can write down the inverse. So is this point clear? If AB is invertible, so there is a quantity C such that ABC equal to CAB and so on equal to 1, then of course BC is an inverse for A. So if
BCA equal to 1 out of that.
What is the left inverse?
let's do that. AB equal to BA, huh? What do I want to prove?
So BC is the right inverse.
One second. So AB equal to CAB equal to 1. Okay, fine, but okay. So yeah, so I want to prove this is equal to 1. Let us multiply by A from this side and B from that side. Okay. No, is this enough? If I prove this, what? Now I want to prove that AB has this inverse C, then I want to prove that A has the inverse.
B may not be commutable with C.
That's what you must observe.
No, but I must prove that. So A minus alpha d and one second. So C B A equal to B A C equal to 1, and now I want to prove B C A equal to 1.
See, B has both right and left inverse. That's all I
Huh?
know. CA is a right, one side inverse.
Yeah, meaning it is a manipulation around this. This implies that now, of course, yeah.
Listen to what he's saying, no, Parthor.
Huh?
And previously, those 4 lines you have written,
Yeah.
B, would you please?
Yeah, it is done. So this implies BCAB is B, and now you have multiplied by AC from this side, it cancels and it becomes 1. It is done. So
He's just saying that you said in those 2 lanes that B has a definite inverse.
anyway, it's a triviality. I am saying it is a triviality. You multiply this by B from this side, it is B, and now you multiply by AC from this side, it is BAC, it cancels because BAC is 1 and this side BAC is 1. So it says BCA is equal to 1. Yeah. So anyway, you do that, and then this implies lambda is in spectrum of PA. And proposition is the following, that I forgot to make the crucial remark. Anyway, after this thing that Barrack algebras, it is after this observation that in a Barrack algebra, if every non-invertible element, every non-zero element is invertible, is C, that says that a Barrack algebra cannot be a field the Barrack algebra other than C cannot be a field, but it could be integral domain. So let us give an example. So consider functions f which are defined on the closed disk to C such that f is continuous and restricted to the interior of the disk. The open disk is holomorphic. Then this is an integral domain. So because if you take two functions which is 0, then that will imply that one of them is 0. Yeah. So now we come to proof of this. Suppose lambda belongs to spectrum of A, that implies by that observation lambda n belongs to spectrum of An, that implies mod lambda n is less than equal to norm An. So therefore, the spectral radius is less than equal to liminf of this. And open disk in C with center 0 and one by RA. Then if okay, so firstly,
And you allow it to be infinity also.
which one to be infinity?
1
Yeah.
by RA.
1 by 0.
I'm just saying, 1 by RA, you allow it to be infinity also.
Yeah. Sure, no problem.
No, all are not equal to infinity.
Less than or equal to 0.
If RA is 0, you will call the radius to be infinity.
Exactly. So f of 1 minus lambda A inverse, this is, it is just a, otherwise it will be whole of complex plane, that's all. This is analytic on omega. Point is that if lambda is this region, that means therefore this admits this expansion and if then in that region this is like that, and so by comparing we get Zn equal to by comparison. So, that series converges. So, for all lambda in omega, lambda n f of a n goes to 0 as n goes to infinity, and therefore, this sequence is bounded for all f in A star, therefore, is norm bounded, and so it says norm a n less than equal to m by mod lambda power n for some m. M may depend upon lambda. So, where lambda is arbitrary, only condition is that since it can go as close to 1 by Ra, this implies which one? This one? Which one? This quantity? Yes. Is this quantity 1 minus lambda A inverse? That's what I mean. If lambda is less than the 1 by spectral radius, we proved this function is analytic. So, if it is a linear functional, now you hit it by that definition. It is in that proposition while proving that the spectrum is non-empty, and argument is always going to this geometric series. Only non-trivial idea is using the Liouville's theorem. Okay. So, this thing is also right. If lambda could be arbitrarily close to this 1 by Ra, and therefore 1 by mod lambda will be kind of arbitrarily close to Ra. So, lim sup of this is less than or equal to Ra. Okay. Next we need another concept. So, suppose I have a function. So, f is a function from suppose C I is the unit interval, this is the unit interval, and E is a Banach space. So, C is rectifiable if this quantity, I take arbitrary partitions P, and then if I do not need rectifiable curves in Banach spaces, I need them only in C. So, I do not, okay. If this is finite, then we call this curve to be rectifiable, and suppose I have a function from an omega to a Banach space E, where E is a Banach space, omega is open in C, and I have a curve in omega then integral FC, or if you like I can put some dummy variables. This stands for the following. So, given a partition P, I consider this quantity Pf, that is summation F C Ti and so this defines a net, and if F is continuous, C is continuous and rectifiable, then this net converges. This is as in the Riemann integration, and the limit is denoted by integral C Fz dz. So, there is a proposition here, and then the conclusion is this. So, you mimic the proof of Riemann integration and so I have a Barrack algebra A, and I have a function f which is holomorphic in a neighborhood of spectrum of x, and so we know that this function, namely lambda going to f lambda lambda minus x inverse, is continuous. So, we can talk of, and C is a simple closed. I will explain this verbally, but I would define it mathematically. Simple closed curve wrapping around spectrum of x once. So, that means the following, you understand the picture and kind of, suppose this is the standard picture, but this picture has a problem, and I will tell you what the problem is. Suppose this is the spectrum and this is an open set on which f is defined, then C is a curve like this. Now, problem with this description is the following: there is no guarantee that spectrum will come in a piece like that. So, there may be part of spectrum is here and part of spectrum is there, and the open set is union of these two. This is also allowed. In that case, C is a union of curves like this. So, given any compact set and an open set containing that compact set, I can always draw curves like this, and C is one such curve. Once you have fixed that, then we can define quantities like integral this function is continuous, so again these are limits of sums like this, and this is the definition of f of x. This does not depend upon the choice of the curve C. That means we need to prove that if we are given two curves C1 and C2 and then these two quantities are same, proving that is same as proving for all phi in A star, these quantities are same, phi of this integrand now of course phi completed this is an analytic function, so this is an analytic function and therefore these two are same. So again this in same this term comes into action, this curve wrapping around sigma x once, that will imply that those two are homotopic. So this assignment f going to fx is a homomorphism on this is the function defined on a neighborhood of sigma x. And 2, if you consider this function, that if f of z equal to z power n, then f of x equal to x power n. We will prove that, but before I do that, I write down my favorite exercise. So let T be a matrix, then the characteristic polynomial is defined as and now I have to prove that so use this proposition, in fact, yeah, this proposition and this definition to prove that, yeah. So let f and g be two functions holomorphic functions defined around spectrum of X, and so here is spectrum of X, and you draw two curves, C1 and C2, but C1 is within C2. That is very crucial. And now let us try to compute this. So you write down lambda minus x inverse as like 1 by lambda minus x, and mu minus x inverse as mu minus x, and this is like this is a rough calculation, but you follow the rough calculation, it is useful. So, because it will kind of help you to remember the formula. This is like 1 by mu minus lambda, lambda minus x inverse minus mu minus x inverse. So, the formula is the following, that this is called resolvent identity. So, So, two things are happening. Firstly, I am freely changing order of the integration. Again, that is justified by this uniform continuity of all these objects and Riemann integrability and so on. And secondly, this curve C1, lambda is a point here and mu is a point there. So, this integral is g lambda. So, this first quantity is 2 pi I f lambda g lambda lambda minus x inverse d lambda, and this quantity is 0 because mu is outside that curve. So, this integral is 0. And this is same as f dot g at x. Finally, you fix a circle of large radius, centered at 0, then so integral this sum is uniformly convergent on these things, so you can interchange order of those things. So, this is equal to summation over k integral and only k equal to nth term will survive. Yeah. So, this proves that it agrees with the ordinary thing. So, point of this is the following, that if you have so it says that in an ordinary algebra, if you have a polynomial p, then you can form these elements pa, but in a Banach algebra, if this is associative algebra,
You don't want to start from
0,
zero?
0, sure. So, arbitrary polynomials you can form, and then in a Banach algebra you can form, if f is a holomorphic function around spectrum of A, then you can meaningfully define f of A, and this definition extends this definition. That means that either you form by this prescription or this prescription you form the same object A. Yeah, that is the point of this, and this is quite useful. Maybe I don't know, in the last week it may come. Stop here. But do that exercise on every matrix satisfies its characteristic polynomial. It is very nicely done this way.
In that thing you showed CAB is 1, BAC is 1. So therefore there exists a left inverse for B as CA and a right inverse AC. So CA is equal to AC, so AC commutes with A.
That is right, but that is not the point of this theory, kind of. It is a trivial remark. You can, yeah, sure, sure. Maybe I should just write down one more exercise, because then whatever we do next time will be more relevant. So on this Barrack L1R, tricky exercise. If you cannot do it straight, then of course we will make it a structured exercise tomorrow. So what are homomorphisms from L1R to C? Huh? So what are homomorphisms from L1R to C? Okay. So maybe I write down the steps. Firstly, suppose phi is a homomorphism, then phi is in L1R star, and you can identify this with L infinity R. Phi of f is integral fx beta x dx. Then you prove firstly beta satisfies this functional equation, and secondly you prove beta is continuous. Then using these two you conclude that phi must be of the form for some t. But this is a nice exercise, and because then whatever I do next time will become an extension of this idea.